Welcome to 16th lecture. We will study power amplifiers from this lecture onwards, and we'll study four types of power amplifiers, namely class A, B, C, and D types of power amplifiers. The difference between the small signal amplifiers that we have been studying in our previous course EDC and these power amplifiers is that they are used to supply power to the amplifier, power to the load, and these are actually connected to the in the output stage of a cascade of a multi-stage amplifier chain, and they're used to drive a speaker most of the times. So power amplifiers mainly they drive speakers, so we need maximum output power at the output at this amplifier stage. So class A is the first type of power amplifiers that we will study. Right, so class A amplifiers they're more like small signal amplifiers, but in the sense that they use the active region of the curve, characteristic curve, but they are different from small signal amplifiers because they use most part of the AC load line compared to compared to the small signal amplifier. So that are the similarities. This is the similarity. The similarity is that they both work in active region throughout their operation. This is a similarity between the class A and the small signal amplifier, and the difference is that class A amplifier, it works on larger part of the load line, AC load line, compared to the small signal amplifier. So there is one similarity and one difference. So let's move ahead. Class A amplifiers, they work in active region. We have already studied, and they supply power to the load. Right. So the difference between the small signal and the large signal amplifiers is that small signal amplifiers, they use portion of load line, whereas class A amplifier, large signal amplifiers of class A, they use the complete load line. Small signal and large signal amplifiers, they both are class A amplifiers. I have already discussed it. The small signal, large signal they both are class A amplifier, and they both work in the linear region at all times. They don't go into saturation. If we draw these characteristic curves, they both operate in the linear region. So suppose we are working with this IP, so they both work in this region, the active region, this region. So we'll discuss it further as we move ahead. Heat dissipation is a small topic that we will cover, that power amplifiers, they need to dissipate heat because they're working at large power. So collector terminal has to dissipate heat because it is the hottest terminal. So we use heat sinks. Heat sinks are common. They are the metallic objects with small input area and the large output area. So they take heat from the input area and they dissipate it to the environment from the larger area. Right, heat sinks are common with the use of power amplifiers. So next we'll see how would a power amplifier of class A work compared to the power amplifier compared to the amplifier that works on small signals that we have been studying. So this is the way. This is Q point, AC Q point for on AC load line. So this is the largest signal that we get at the output of a power amplifier, whereas for a small signal amplifier, that may not use the whole available region around this VCE. So this is the difference between a small signal amplifier and a class A power amplifier. So class A power amplifier will utilize the whole region available around the Q point. So this is class A amplifier. So it, they both work in the linear region, but small signal amplifier uses may use a part of it, but power amplifier tries to use the whole available range, right? So if we do not put this Q point in the center, maybe if we put Q point here, what can be the problem, right? And if we place the Q point here instead of placing it at this point, what is the difference that we get is that we get the signal clipped from one side, because it wants to go all the way like this, but it cannot go that, but cannot go anywhere beyond this limit, because this is the limit put by the VC max, the VCC, in fact, VC max, VCE cutoff, or VC max, the max possible voltage that the VCE can take. And of course, the max possible voltage that VCE can swing, the output voltage can swing up to the point is the VCC plus VCC, the DC supply voltage. So the output swing cannot go beyond VCC, your supplied DC voltage. So it has to be clipped. And of course, the current would be clipped. And if this Q point is biased towards this, the upper end, this one, so we'll get an output signal that will have a full swing on this side, but will be clipped from this side. So that's the reason we should have the Q point in the middle. So keeping, if you want to use the whole available range around this Q point, we have to select this Q point in the middle. I mean, it should be equal to VCEQ should be equal to VTT by 2. VCEQ should be equal to VTT by 2. It should be in the middle, right, in the middle, so that we can use the whole range. If we don't do that, the signal will be clipped either from the lower side or from the upper side, which of course we do not desire. So we have good reasons to keep this Q point in the middle of VCC, that we normally do for class A amplifier, so that the whole range can be utilized, right? The last topic that we will study in this lecture will be the power gain. Power gain is the ratio of the, and of course it should be, the power gain is the ratio of the output voltage to the input voltage. And if it is a class A amplifier, the output voltage would be the voltage drop across this load RL, and the power dissipated can be computed using this formula, VL squared over RL. We studied in linear circuit analysis, the first course on electrical engineering. And Pn would be Vin squared times over Rn. If we have this, if we complete this circuit like this, we have a source R in here. So the input power would be this Vin times the input resistance that we see when we look into the base terminal right here. So we see this R1 grounded for AC, this is grounded, this R2 is grounded. So these R1 and R2, they come in parallel in there, and they come in parallel with beta times this small Re. We will not include this capital Re here, because we know that with this capacitor, which capacitor? This capacitor, we bypass this Re, and it is no more being seen by the AC input, because the AC is bypassed using this capacitor. We have already studied that. So P in is now AP is P out over P in. So let's plug the formulas for P out and P in here. P out is this, P in is this. Right, if we put this and solve a bit, it comes out to be AV squared Rin over RL, where AV is the voltage gain. Voltage gain is, this is because we have VL squared over Vin squared. So VL over Vin whole squared, this gives us AV squared. So AV squared Rin over RL. So this is actually the voltage gain of the amplifier. We know the voltage gain of A BJT common emitter amplifier with RE bypassed with the help of a bypass capacitor is RC in parallel with RL and RC in parallel with RL divided by small RE, because this capital RE is bypassed by the bypass capacitor. So that we will study in the lectures to come. And the AP can be computed like this: AB squared Rn over RL. So we know RL is connected at the output, it should be given, and Rn can be computed using this formula. It's actually a recap from the last course, EDC, electronic devices and circuits. So it's a recap. It's a recap from EDC. And then we have to solve an example that AP is given to be a 1. It's not AP, it is AV. We have to compute AP. This is AV, the voltage gain is given to be a 1. Rn is 5K, RL is 100. So we have to find AP. That's simple because we have to plug all the values in AV, Rn and RL. Everything is given, and AP comes out to be 50. Right. In our next lecture, we'll continue studying Class A amplifier, and that's all for this ECD16. Thank you.